the main thing that we still have left to do is to prove that if we've got two maps that are homotopic to each other, then they have the same effect in homology. And so the proposition on this slide is going to be a warm-up for that. It'll be we'll prove that fact on the next slide, but we need this preliminary proposition as input to that. So here we've got two symmetrical complexes K and L, and two maps P and Q from mod K to mod L, and that are both continuous. And we're going to suppose that they're very close together. Okay? And we're going to prove that if two maps are sufficiently close together, then they have the same effect in homotopy. And how close do we need? Well, it depends on the dimension of the complex L. So we're going to suppose the complex L has dimension E, and then the condition has got to be that the distance between P and Q is less than 1 over E plus 1. More specifically, that for every point X in the realization of K, the distance from Px to Qx is going to be less than 1 over E plus 1. And then the claim then is that there's a pair n, f that is a simplicial approximation for P, but it's also a simplicial approximation of Q. So that means that we can use the pair n, f to calculate P star, and we can use the pair n, f also to calculate Q star. So P star and Q star are actually the same. Okay, so this is going to be another argument with Lebesgue numbers of appropriate coverings. So what do? For each point B in the for each vertex B of L, we're going to let UB be this thing here. It's going to be an open subset of the realization of K, and it's going to be the preimage under P of the open star of B intersected with a preimage of Q under the open star of B. In other words, it's a set of points X such that Px and Qx both lie in the open star of B. Okay, so P is continuous, so this set here is an open set, and Q is also continuous, so this set here is also an open set. It's an intersection of two open sets. That's an open subset of the realization of K. And we want to claim that these sets UB, that they form a cover of mod K. Okay, so to see that, let's choose some point X in the realization of K. We need to show that it lies in one of these sets UB. So for this we need to look back to the proposition 9.35, which we had a while ago. That says that if we look at the covering of mod L by open stars, well, you know, that is an open covering of the compact metric space mod L, so it has a Lebesgue number, and we show that actually this specific number, 1 over E plus 1, is a Lebesgue number for that covering. So that means that, yeah, if we look at this open ball of radius 1 over E plus 1 around the point Px, then that's a ball of radius less than the Lebesgue number, and so it's contained in one of the sets of this open star covering. So we can choose some point B with the property that the open ball around Px of radius 1 over E plus 1 is contained in that open star of B. Okay, so in particular, I mean, the point Px, of course, lies in this ball, so it lies in the open star. But also, we've got this hypothesis that the distance between Px and Qx is always less than 1 over E plus 1. So distance from Px to Qx is less than 1 over E plus 1, so that means that Qx lies in this open ball, and so this point Qx also lies in the open star of B. So both Px and Qx lie in the open star of B, and so by looking back to the definition of UB, we see that X is a point in UB. So now we've seen that these sets UB, they're open subsets of mod K, and they cover all of mod K. And again, mod K is this is a compact metric space, so this covering by the sets UB is going to have a Lebesgue number. So we're going to choose a Lebesgue number for that and call it epsilon. Now we want to choose n large enough so that the mesh of barycentric subdivision map beta bracket n is less than this epsilon. So we've got the map beta bracket n from k bracket n to k, and we want to make it so that the mesh of that is less than epsilon. And because we had this proof earlier that composing with beta reduces the mesh by a factor of d over d plus 1, where d is the dimension of k, and so if we do that often enough, we'll get the mesh down below epsilon. And so that has, if you've got everything in the open star of A, then that's going to be within it's going to be within in a kind of common simplex with A, and you know that beta n, so, because of this mesh business, that's going to keep everything, the image of beta n of anything that on a common simplex with A is going to be distance at most epsilon away from A. And so this set here, this image under beta n of the open star, that's going to have a radius at most epsilon, and so it's going to be contained in one of the sets of this open cover by these UBs. So we can choose a vertex FA and FL with the property that this set here is contained in U subscript FA. And so let's just recall what that means. UFA, remember, is the intersection of these two pre-images. So what that's saying is that P composed with beta n sends this open star here into the open star of FA, and also that Q composed with beta n also sends this open star of A into the open star of FA. And so this first thing, that's the condition for F to be a direct simplicial approximation for P composed with beta n, and this thing is condition for F to be a direct simplicial approximation for Q composed with beta n. So both of those things are true, which means that that the pair n, f is an indirect simplicial approximation for both P and for Q, and so we can use this pair n, f to calculate P star, and also use the same pair n, f to calculate Q star. So P star and Q star are the same as claimed. So now from that, we want to go on to prove this, that if you've got two different maps P and Q from mod K to mod L, both continuous and homotopic to each other, then we want to prove that P star and Q star are the same. Okay. So the idea is basically like this. Okay, so we've got some homotopy H from so that's a map from 0, 1 cross mod K to mod L, and it's a homotopy from P to Q. So you think of this as kind of being a movie which starts at time 0 with P, at time 1 it gives you Q. And the idea is that if we just look at a very short space of time in that movie, then the map won't move very much. It'll move less than this 1 over E, where E is the dimension of L, and so the induced map in homology won't change by the previous proposition. Okay, so I want to be a bit more precise about that. So we're going to make this claim that there exists some delta greater than 0, such that the distance from H of U to HV is less than 1 over E plus 1, whenever these U and V are 2 points in this domain here, and the distance from between U and V is less than delta. Because this is almost just kind of saying that that H is a continuous map. Right? If we allowed this delta to depend on U, then this would just be saying that H is continuous. But here we said that there exists some delta such that this works for all U, so delta is not allowed to depend on U, so that's a little bit different. But that's just saying it's not continuity, but uniform continuity. So we've got the space here, 0, 1 cross K is a compact metric space, and and if you go back and you look at the metric spaces notes, it's theorem 7.14 there says that if you've got any continuous map between compact metric spaces, then it's automatically uniformly continuous. And and this claim here is just it's just immediately that's kind of part of the definition, an instance of the definition of uniform continuity, which is given us definition 7.12 in the metric space notes. Okay, so we can assume that this delta exists. And then we can choose some integer n with 1 over n less than delta. So then we're going to split this unit interval here, 0, 1. We're going to split it up into small parts, into n subintervals. So we're going to look at these maps Ri. So Rix is h of I over n comma x, so 0, I between 0 and n. So we've got n plus 1 equally spaced maps as part of this kind of homotopy. So if you look at distance between I over n comma x and I plus 1 over n comma x, that's less than delta. And delta was chosen so that when you've got 2 points separated by less than delta, that means that the images under H are going to be separated by less than 1 over E plus 1. that's how we chose our delta here. So we're saying the image of this under H is Ri of x, and the image of this under x is Ri plus 1x. So what we're saying is that Ri and Ri plus 1, they're separated by less than 1 over e plus 1. Okay. And so by the previous proposition that we had on the previous slide, that's showing us that, that the Ri and Ri plus 1 give us the same map in homology from the homology of K to the homology of L. Okay. But yeah, so R0 and R1 are the same, R1 and R2 are the same, R2 and R3 are the same, etc. So that tells us that we chain those together, R0 star and Rn star are the same. But H was just a homotopy from P to Q, so we put H of 0x is just Px, in other words R0 is P, and similarly Rn is Q. So what we're saying is that P star and Q star are the same.